Okay, in this lecture we are going to discuss about the division algorithm. Division algorithm. Division algorithm. Now, according to this algorithm, it says that if A is any integer and B is any positive integer, then there exists unique integer Q and R such that A equal QB plus R, where A and B belongs to, you can see, belongs to Z, and R is greater than equal 0 and R is greater than equal 0 and it's less than B. So A, B belongs to Z and you can see B is greater than equal 0. And now we are going to prove the division algorithm. So first, to prove division algorithm, we have to look at the outlines of the proof. So first we have to prove that R is greater than equal 0, then R is less than B, and again you can see there exists unique integer Q and R. So we have to prove that Q and R are the unique integer. Okay, now first to prove, let here, this is the proof. Let R is a set S such that which is equal to A minus XB such that A minus XB is greater than equal 0 and where X is belongs to Z. Okay, see, to prove the division algorithm, we are going to apply the well ordering principle. So to applying the well ordering principle, you will know that the set must be non-empty. So to see that the set is non-empty, let here you can see that A and where B is belongs to Z and B is greater than equal 0. Okay, it is given that B is belongs to Z and B is greater than 0. So from this you can see B is greater than equal 1. Okay, now from this, if we multiply both sides by modulus A, then you can see the result. So multiplying both sides by A. Okay, now from this you can see that A minus XB. See, if we putting X equal minus modulus A in A minus XB, then you can see here A minus XB is equal to A minus minus modulus A into B. Now from this we can see that it will be A plus modulus A into B. Now see, both modulus A and B are positive, so A plus should be greater than A plus modulus A because B is positive. Now you can see that modulus A and modulus A plus A must be greater than equal 0 because it cannot be negative. Okay, now from this we can see for x equal minus modulus A minus xb is greater than equal 0. So from the definition we can say that is A minus xb belongs to S. Now see, so we can say that S is not a empty set. So if S is not an empty set, by the well ordering principle we can say that S has a least element. So by the well ordering principle, S has a least element. Okay, now we call it R. And such that for some x equal q belongs to Z, we have so R equal to A minus QB, which is greater than equal 0, and from this we can see that R is greater than equal 0, greater than equal 0. Now the next step we have to show that R is we have to show that R is less than B. Now suppose this was our first step, first outline. So now suppose R is greater than B. Okay, now from this you can see R minus B will be greater than equal 0. Okay, now from this we can see R equal A minus QB. So A minus QB minus B greater than equal 0. Okay, now from this you can see that R minus B equal to A minus QB minus B is greater than equal 0. Okay, now from this you can see that R minus B equal to A minus Q plus 1 into B is greater than equal 0. Now from this we can see that A minus Q plus 1 times of 1, so B, which is greater than equal 0, and from this we can see because R minus B equal A minus Q plus 1 into B, so we can say that A minus Q plus 1 is less than R, and because of it is greater than equal 0, so we can say that a minus q plus 1b belongs to S. Okay, so that's now this contradicts the well ordering principle. So this contradicts the well ordering principle. Well ordering principle. So we can say that R must be less than B, R less than B. So we have found a pair of integers, Q and R, which R is greater than equal 0 and less than B, such that A equal QB plus R. Now the next step we are going to show that the Q and R are the unique integers. Okay, now suppose we are going to check the uniqueness. So suppose there exists another pair of integers Q prime and R prime such that R prime is greater than equal 0 and less than B, and A equal Q prime into B plus R. Now suppose R is greater than R prime, greater than equal R prime. Now from this you can see R minus R prime should be greater than equal 0. Now since A equal QB plus R, and from here Q prime B plus R prime, so from this we can say that Q prime B minus QB equal to R minus R prime. Okay, but you can see that R minus R prime is greater than equal 0, but you can see R minus R prime is greater than equal 0, so Q prime B minus QB greater than equal 0 because it is equal. So from this you can see that Q prime minus Q to B greater than equal 0, and the Q prime minus Q must be less than B. So from these two statements we can say that Q prime minus Q to B is greater than equal 0 and less than B. From you can see from this line. So from here you can see we can simply divided this B by this B, so we can see that it will be Q prime minus Q. If we divided B and this B by this B, because it is a positive integer, okay, we can simply divide, so it will be less than 1. So you can see here that Q minus Q is also a integer, So find the number that which satisfy this condition. Okay, which is equal to 0 or greater than 0 or less than 1. So from this situation you can see that the number which can satisfy the condition that q prime minus q must be equal to 0 only. So I write the statement again here: 0 is equal to q prime minus q and b and less than b. Okay, now from this we can say that q prime minus q b is less than 1, and from this we can say that q prime minus q equal 0. So from this we can say that q prime equal q. Thus so this pretty easy to prove that we can see r equal, now we know that r equal a minus qb. Okay, and you can see that q equal q prime, so we can put a minus q prime b, so it is equal to r prime. So you can see that r and r prime and q prime are not different, so it is they are the same number. So you can say that we have thus we have found that there exists a unique pair of integers q and r such that r is greater than equal 0 and less than b, and a equal qb plus r. So this was the proof, and you have to first remember the outlines and then practice it. Okay.